Hello and welcome back to Hell 1. I'm a Calculus 1, section 5.2 on definite integrals. So we are going to take a look at the approximation, but now this approximation is going to be turbocharged so that we can have the exact area under the curve. So what we learned last time is that we can cut the area under the curve and create left and right triangles, and that will produce error. Now, I'm not going to do it in all of these. I'm just going to focus on one of these. What I'm going to do is I'm going to cut. So let me first create a rectangle now. So this let's use black for the first. So I'm using the right-hand sum in this case. And we see how much error we have. What I'm going to do next is I'm going to do and cut this area in half and draw another right rectangle here and a right rectangle on the top. Now, do you see that we eliminated this much error? That's eliminated now. Is no longer error because the new rectangles are skinnier, and because they're skinnier, yes, right, there's more, exactly. Now, what happens when I cut each one of these, let's say in half? You can cut them in any many you want, right? So if you are to cut each one of these in half, you will eliminate even more error. So every time you put more and more and more and more rectangles, you eliminate more and more error. So what happens if you are to use infinitely many rectangles? Well, those infinitely many rectangles would be infinitely thin. And in some sense, they would fit underneath each point of the function, and they would cover the entire area exactly with no error, because remember, they're infinitely thin. So there is nothing to go over the line or under the line. It's just going to be sitting on the line. So I need you to look at this argument of exact area. So we said that the height will be computed at xi, and this is your xi, and this is your delta x. So, to have my one rectangle, I'm just going to have f of xi times delta x. So this is my one area. Now I'm going to introduce summation symbol, which looks like this, sigma. And I'm going to say the counter will start at 1 and go to n, which is as many rectangles as you want. This is many rectangles. And this is equal to 5.1. If your n is 4, you will have 1 to 4, 4 rectangles. But now, to get exact area, I need to send this n to infinity to make sure that I'm using infinitely thin rectangles, so there's no error. So now I add in front the limit, n goes to infinity, and finally, this is the statement for infinitely many rectangles. And that's equal to 5, 2, which is now exact area. So it's a very systematic way to build this. You start with one rectangle and you say, okay, let me add a whole bunch of more, and then let me make that into infinity so we can actually have exact. So it's built in stages. But the formula is just one formula. So now I get to write that the exact area is equal to the limit summation f of xi delta x, where I goes from 1 to n, and n goes to infinity for the limit. This is what it's going to give us exact area. Now, before we go there, I need to talk briefly about this symbol summation and the properties of summation, because you probably never seen that before. So this symbol is a Greek symbol. It's a Greek letter. It's called sigma. It's just a capital S in Greek language. And it stands for summation, for addition. And what this is just a lazy notation for us, so we don't have to write same thing 15,000 times. It's using the counter I, or J, or N, whatever you want to use as a counter. And the way it works is you say I starts at 1 and ends at 5. And let's say you have I squared as a formula inside. So your I is 1 on a first run, so I squared, plus 2 squared, plus 3 squared, plus 4 squared, plus 5 squared. You have to run through all of the integer increments from 1 to 5, and you have to plug those into the formula that contains this I. And now you can compute this, right? It's 1 plus 4 plus 9 plus 16 plus 25. So that's 30, 40, 55, right? 30. Oh, no, actually, it's easier. It's really go 10, 20, 30, 55. Yes, okay, good. So, 55. Our previous formula was, look at this, delta x f of x0 plus delta x f of x1 plus delta x f of x2 plus delta x f of x3. That's annoying. What I can do is I can factor out delta x, and then all of these f's I can put into f of xi, and then say I is going to start at 0 and end at 3. So I is the counter which takes on all of the values from 0 to 3, 0, 1, 2, 3, and every time when it switches the value for I, it creates a new term, and each term is added. There is the same thing for multiplication with the capital pi, right? So if you add like pi of I, let's say plus 2, then you would have I 0 plus 2 times 1 plus 2 times 2 plus 2 times 3 plus 2. So there is a symbol for multiplication as well. Now we're using only for addition, so we're good to go. So you can have any formula. You can have any formula, and you can express that formula in terms of summation, so it's not annoying. And now you can move this delta x, right? So you can say times delta x on the other side. So summation symbol is simply this. Now one of the properties that we want to know is that summation, let's say I starts at 0 and goes to n, whatever, of f of some I plus or minus g of some I. You can break this into separate sums. So that's what we have. Oh, plus minus. If you have plus, it's plus. If you have minus, it's minus. Counters and everything stays the same. So we can break it apart. If you have plus and minus, so product you can't, and division you can't, but sum and difference, sure. So now that we know all of these things, we can find the exact area under f of x equals, let's say, 3x plus 4 on the interval 0 to 5. Can you do this question using geometry? Sure. Graph 3x plus 4 and just cut it off at 0 at 5 and just see what the area underneath is. It's you're going to get some kind of trapezoid, and you just, you can cut that into a rectangle and triangle and then figure out. So it should take you a minute. But why simple if we can complicate things, right? So what do? We first set everything up. Remember what I have. I have limit, summation. Well, limit n goes to infinity. Summation, it goes 1 to n. And inside over here, I have f of xi times delta x. So need both of these. So we start by figuring out delta x first. I don't know why I'm dramatic, but which is b minus a over n. And in our calculation, that's 5 minus 0 over... No one ever specified how many. Guys, n is going to be sent to infinity. So we actually get to drag this 5 over n through our calculation. So what's delta x? Delta x is 5 over n. Do you remember the xi formula? A plus I delta x. That was in the last section. So now this is 0 plus I 5 over n, which is 5 over n. I don't need this parentheses. I is not a complex I. So I'll write that. I not complex. So don't confuse that. It has nothing to do with the square root of -1. I, in our case, is a counter. I is a counter. 0, 1, 2, 3, 4, ... forever. There we go. Finally, my f of xi is going to be my function when you plug in xi that you got. So my function is 3 times my xi is given as 5 over n I plus 4 at the end. This is 15 over n I plus 4. This is the setup. All you need to do now is to plug this into the limit and compute. So what do? Well, plug everything into the limit. We have limit n goes to infinity, summation 1 to n, and now you have here, instead of f of x, you have 15 over ni plus 4, and all of that gets to be multiplied by dx delta x, which is 5 over n. So this is what we have for our problem. So now, when you go back, the only thing that you can do is distribute 5 over n. So limit n goes to infinity, summation 15 times 5, 75 over n squared I plus 20 over n, in parentheses, because summation needs to operate on all of them. And then you go and you separate these using the rule we just covered into different sums, but you still have to have limit n goes to infinity available for all of them. So now you have to put parenthesis there, summation of 75 over n squared I, where I goes from 1 to n, plus summation of 20 over n from 1 to n on the second one. Then we get to kick in front of the summation anything that has no I variable in it, because it's constant. So we have 75 over n squared summation of I goes from 1 to n, plus 20 over n gets kicked out, and now you have summation of just 1. I goes from 1 to n. So when you kick everything out of the sum, 1 has to stay within, because it's a placeholder, right? When you multiply back in, you're in. So now, on page 345 in your textbook, there are 4 equations given in a chart which convert summations, and the book is using k's, I'm using i's. It's the same thing. You have summation of I, which is the same as summation of k over here, and you see that that turns into n plus 1 over 2. So that's when you add all of these numbers, that's what you get on the other end. So using this table, we now have 75 over n squared, and this becomes, the sum becomes nn plus 1 over 2. So that was page 345. Now the second one over here is 20 over n, and this one becomes n. Again, table. Page 345. Now, I get to cancel these ends. I get to cancel one of these ends. And I have to deal with the limit from chapter 2 now. That's easy. So I have 75 n plus 1 divided by 2n plus 20. These exponents are the same, so we just take front coefficients. I have 75 over 2 plus 20. That's 4115 over 2. And that is the exact area. Exact area on the linear. Sometimes this linear produces just a triangle. It will not be any shorter to solve, but you can look at the picture and you just know it's a triangle, so you can just cheat, right? Off of it. So what you have seen is the procedure that is equivalent to your procedure for finding a limit using the age equals 0 f of x plus age minus f of x over age. Remember that one? Or you kind of blocked that one in your head. So that was the limit definition of the derivative. This is something like a limit definition of the integral. And it's a little bit spicier, right? So if the simple case looks like this, what would be any tougher case look like? And the answer to that is just hell on earth. So is there an easier way to deal with this? And the answer is yes, because it turns out that our integration solves this problem in one line. So it turns out that exact area under the curve is the integral of this function, 3x plus 4, dx, and then we just specify that we want to go from 0 to 5. What was the integral? Yeah, 0 to 5. We put those in limits. So now, when you have this thing, you do your regular integration. What's the integral of 3x? It's 3x squared over 2 plus 4x, and this is new now, no plus c, we put the vertical line 0 to 5. So now, I will give the formula for this. So now, we have 3 halves, and the way to compute this is you plug the upper limit first, so that's going to be 5 squared plus 4 times 5, and then minus 3 halves, 0 squared minus 4 times 0, which will give me 3 halves times 25 plus do we remember seeing 75 over 2 plus 20 to give us the same answer of 115 over 2? And now we can do the same game as when you go to your eye doctor. What's better, A or B? Right? That's how they ask when they keep changing the lenses. A or B? A or B? So it turns out that integral is the one to calculate exact area. There are some limitations. We'll see that your integral is not allowed to go under the x-axis and blah, blah, blah. But for now, this is good enough. We'll deal with that next week. So area is equal to the integral from a to b of f of x dx, which is calculated as the antiderivative f of x computed from a to b, which is f of b minus f of a. This is called the definite integral. That's called the definite integral. So I just want to connect these things. Integral from a to b f of x dx. Are you ready? Limit summation f of xi delta x. Do we know from our previous case that in here there is a multiplication? Actually, let me go further a little bit. Differentials. Do you remember that dx and delta x are the same thing from differentials? That's in your exam, right? So from differentials, we know dx and delta x is the same thing. We also see a multiplication here because that's the length and the width or height of the rectangle. So there has to be a multiplication in our integral as well. What does this symbol for integral, what does this symbol remind you of? Come on. What does it remind you of? Does it look like anything? How about if I make it shorter and a little bit fatter? How about if I make it a little bit more short and a little bit more fat? What is going to become? What does it become? Exactly. It just becomes the letter S. And what S stands for? It stands for hope on Krypton, right? So S stands for summation. And that's this. The original Riemann notation was, I gotta look this thing up, was either SPU or SUP. So it's one of these two was his original notation for integration. In time, we just invented, let's stretch out this S, all right, into a squiggly line. That's what it is. It's a stretched out S. And now, if you compare these two, you see that this over here is technically just a lazy notation for this. So when you are talking about, someone says or mentions Riemann integral, looking at the German mathematician Riemann who figured it out, you say that the definite integral a to b f of x dx is equal to the limit n goes to infinity summation I goes from 1 to n of f of ci delta x. It's called the Riemann integral. And the calculation for the Riemann integral is all of this stuff here. So now, almost 300 years later, we have shortcuts for it, which are called integrals. And we don't have to go through that entire painful calculation that was there, shoveling those sums and working out all of those, right? Because now we can just integrate and be done. There are limitations, though, so you have to be very careful. So this is going to be the last problem for today, and then we're going to pick up next week after the test and finish this off. The first thing that you have to worry about here, well, actually, let's do this. Integral 0 to 2 pi sine x dx. Now, you know that you can color, right? Use a color pencil or whatever, and you can color under the sine graph. So you know that area exists because you can color. You can only color on area. Like that wall is green. You have to have that wall with the area exposed to paint the green. So you know that if you draw sine x, there is some inside area under the curve and you can color it. Now let's take a look at a calculation. What's the integral of sine? Negative cosine. Very good. Integral of sine is negative cosine. And then we have to compute that from 0 to 2 pi. So what happens now? We get negative cosine of 2 pi minus negative cosine computed at 0. So this minus is from the formula. And the other minus signs they belong to cosine. So how much is a cosine of 2 pi? It's 1. So I have negative 1 plus 1, and I get 0. So this calculation said to me that area under the sine curve is 0, and I know it's not. Because I can see it. I can color. Right? So if I draw the period of sine between 0 and 2 pi, well, I can take the color and I can paint. So is the area 0? I know it's not 0. There is area. So we need to address this issue. So here in blood, when calculating exact area under the curve, f of x must not go below x-axis. If it does, treat the affected area with absolute values. And this is where we get to fix our problem. I know that the sine x is going to dip below x-axis between pi and 2 pi. So, to find the area 0 to 2 pi of sine x dx, I have to break that 0 to pi of sine x dx plus the absolute value of the integral pi to 2 pi of sine x dx and closed absolute value. Because that's the part which will give me the negative, which would cancel the other one, and that's why they're 0. So now, if I recompute my sine, I get 0 to pi, when I integrate. So when I compute this now, I have negative cosine x from 0 to pi plus absolute value of negative cosine of pi to 2 pi. So I have a negative cosine of pi, minus and minus give me plus cosine of 0. And then the absolute value kills the negative, so it's a plus cosine 2 pi, and finally minus cosine of pi. which is equal to cosine of pi is -1, so negative -1, plus cosine of 0 is 1, plus cosine of 2 pi is 1, and then minus cosine at pi is -1. So I have 1 plus 1 plus 1 plus 1 equals to 4. Area under sine graph is 4. It's a whole number. Oh, come on, you're all dead inside. Think about it. You have the trig, you have all these pi's and 3.14 and everything is irrational and trigonometry and you're going crazy. Area works out to be 4. It's not 4.3 or pi squared or anything like that. It's 4. It's awesome. Which means that each bump of sine is 2 each, right? Because they're symmetric. Each bump is 2 in area. And it's, in my never humble opinion, really cool thing. So we'll pick up on this and solve more examples next class. It's time for us to talk about the exam. So restart the stream in 17 seconds and count.